resting potential, the plasma membrane has a positive charge outside of the cell and a net negative charge inside of the cell. This charge difference, called the resting membrane potential, is the result of ions moving into and out of the cell. The concentration gradient and permeability of the membrane to each ion first establishes the resting potential. There is a higher concentration of Na+ ions outside of the cell and a higher concentration of K+ ions inside of the cell at rest. This is because upon phosphorylation, sodium-potassium pumps pump out 3 sodium ions and 2 potassium ions against their concentration gradients. Thus, there is a lower number of positive ions inside of the cell than there is in the outside, which gives it the net negative charge. This process is how the resting potential is maintained. Additionally, through the ungated potassium leak channel shown here, facilitated passive diffusion can take place as potassium ions move back out of the cell through that transport protein. This is because diffusion takes place from an area of higher concentration to lower concentration. Although most protein channels are closed, such as the sodium channel, the potassium channel remains open. Membrane potential can be changed by hyperpolarization or depolarization, but today we'll be focusing on hyperpolarization. Action potential occurs when there's a large change in the membrane voltage caused by depolarization. Beginning with the resting state, sodium ions are concentrated on the inside of the cell, while potassium ions are concentrated on the outside of the cell. The depolarization stage then occurs where stimuli lets the sodium channels open, which allows more sodium ions to flow in. The influx of sodium ions opens more sodium ion channels, allowing more sodium ions to flow in. This acts like a positive feedback loop as more and more sodium channels will open. Then we enter the stage of rising action potential. The threshold is crossed as shown in this graph. Most sodium channels are open and the inside of the cell is very positive while the outside of the cell is negative. This is because of the influx of positive sodium ions into the cell. In this stage, more sodium ions continue to pass through the sodium channels into the cell. In the falling action potential stage, the sodium channels become inactive, while the potassium channels open. This causes an outflux of potassium ions, bringing the membrane back to where the inside of the cell is negative, while the outside is positive because of all the sodium ions. Lastly, sodium channels close and the membrane potential returns to its resting state again. The potassium channel closes as well. But for now, let's get into more detail about action potential at the synapses. At chemical synapses, an action potential arrives and depolarizes the presynaptic membrane. This causes the voltage-gated Ca2+ channels to open, initiating the influx of Ca+2 ions. Concentration of those ions reaches a high value, which triggers vesicles containing neurotransmitters to fuse with the presynaptic membrane. This releases the neurotransmitter into the synaptic cleft. These neurotransmitters then bind to the ligand-gated ion channels. This opens it, allowing movement of sodium and potassium ions.